So today I'm going to walk you through the chapter 14 review questions. These are on the concept of thermodynamics. So like normal, I'm going to be skipping review question number 1 because that's just key terms and definitions. The question number 2 tells us that a reaction is determined to be spontaneous at 25 degrees Celsius. And the question is asking, does that mean that it will automatically happen if you mix the reactants together at 25 degrees Celsius? And it won't automatically happen if it's spontaneous. So the answer is no. Now there are chances that the reaction could absorb enough energy from its surroundings to start, and that energy it needs to start is called an activation energy. But spontaneous does not mean that it just happens automatically. It just means that after it's had its activation energy, the reaction will then proceed. And so just because you mix two compounds together at 25 degrees Celsius does not mean that they will start. They may need to have some activation energy added. Question number 3 says a reaction has a positive delta H, and it's asking, is this reaction endothermic or exothermic? And a positive delta H, if you'll remember, delta H stands for enthalpy, and it is the heat that is either absorbed or released by the reaction. And if it's positive, it is actually gaining heat, so it is absorbing heat, and so that would make this an endothermic reaction. Question number 4 gives me the delta H's for 2 reactions, and it tells me that they're each done in a beaker, and both of the beakers get hot. And the question wants to know which beaker actually gets hotter. And in each of these beakers, we have 1 mole of reactant. So we essentially have the same amount of reactants happening, and they're both releasing heat. And these are both negative delta H's, and that happens when we have an exothermic reaction that's releasing heat. But the one that's going to be releasing the most heat is going to be this beaker because it has a higher amount of energy coming out of it. Question 5 tells us to use bond energies located on page 420 to calculate the delta H of this reaction. And so before you can do bond energies, you need to know what bonds there are. And so we're going to first start by writing the Lewis structures for all of these compounds. So the Lewis structure for CH4 is actually pretty simple because carbon can make 4 bonds. And so it just looks like this. Now the Lewis structure for 3 Cl2s is a little bit different, but we're not going to write it for 3 like Cl2s. It'll just be like ClCl. If you'll remember, chlorine has 7 valence electrons, and so it's just going to share. For the next compound, we're going to remember once again that carbon can make 4 bonds. So off of the carbon, we have 1 hydrogen, and we have 3 chlorines. And then for this next last Lewis structure, we have just hydrochloric acid, and it's a pretty simple one. It looks just like that. So now you can go to page 420 and you can calculate the delta H for this equation using the bond energies. So in the balanced chemical equation, we actually have 3 of these. So I'm just going to go ahead and draw 3 of them on there so you can see it. And we have 3 HCl's also. So if you'll remember calculating the delta H using bond energies, it's just the formula is the energy for breaking bonds minus the energy for making bonds. So I'm going to actually take each of these bonds and look them up on the chart to see how many kilojoules each bond has. So the bonds that we're breaking, we have to break this CH bond, and we actually have 4 of them. So you're going to have 4, and you're going to say times, and I know from the chart that there's 410 kilojoules per mole. And this would be mole after the 4. So it look like this. And moles cancel out, and you're left with an delta H in kilojoules. So now I'm also going to add up the bonds for the 3 Cl-Cl bonds. And the chlorine to chlorine bonds have 243 kilojoules per mole in each. Moles cancels out. And so that's the bonds that those are only bonds we have to break. So now we're going to take away the energy for the bonds that we're forming. In this compound, I'm forming carbon-chlorine bond, and there's actually 3 of these. So you have 3 times 330 kilojoules per moles. Moles cancel out. But also in this compound, we also have a hydrogen-carbon bond, but we only have 1 of those. So I'm going to take away 1 of those. And so that bond has 410, dropped my units for space, but I only have 1 of those bonds there. And so the next thing, I'm also going to take away the energy for these 3 hydrochlorine bonds. Each of the 3 hydrochlorine bonds has 432 kilojoules per moles in it. So when you put that in your calculator, remember that you have to use parentheses in order of operations around all the multiplication parts. So you're adding the bonds that you're breaking, and you're subtracting the energy from the bonds that you're forming. And you should get a total delta H of negative 330 kilojoules. Question number 6 is extremely similar to question number 5. It's calculating delta H using bond energies, but they already give you the Lewis structure for the formation of this compound. So we have 2 reactants and we're acting to make 1 product. But the question is giving us the delta H for the whole reaction. And we're also going to use our chart again on page 420, and they're asking you for the bond energy for this bond. Now we don't have that bond energy on our chart, so we're going to do the same equation we just did, except delta H is not your unknown, the C triple bond N is your unknown. So the first thing I'm going to do is, instead of saying delta H, I'm just going to set it up for negative 137, because that's what they tell me my delta H is. And then I'm going to go ahead and figure out the bond energies for all of the bonds that I'm breaking, even though I still have a variable here. So I have 1 carbon hydrogen bond that I'm breaking, and it's only happening 1 time. So I have 1 mole times, and the 410 comes from that chart. So moles cancel out. Now the other bond that I'm breaking is this carbon nitrogen bond. That's what I'm looking for, and I only have 1 of those. So I would set this up like this. So it looks very similar. I have 1 mole and 1 mole, and I'm just going to use the C triple N as my variable. So the next part you're going to do is you're going to add these bonds, because these bonds are also breaking, and we actually have 2 hydrogen-hydrogen bonds. And the hydrogen-hydrogen bond has a bond energy of 436 kilojoules per mole. So that is all the bonds that you're breaking. So now you're going to subtract the energy that you need to rebuild back all of these bonds. And here I have 1, 2, 3. So I have 3 carbon-hydrogen bonds there. So I'm going to take away 3 moles. And that one is 410 kilojoules per mole. You may have learned that. We use that bond a lot, so sometimes we just learn the number. So the other bond that I am having to make is this carbon-nitrogen bond, and there's only 1 of those, so I'm going to subtract it. This carbon-nitrogen bond has a bond energy of 300 kilojoules per mole. And the next one that we have to look at is this nitrogen-hydrogen bond, and we have 2 of those. And so those each bonds have 390 kilojoules per mole. So now you're going to put that all in your calculator, pay close attention to your parentheses, and you're going to be setting that up a little bit different. We're going to be solving not for the delta H, but we're solving for the CN bond. So you should end up with, and this is kilojoules, 137,000 kilojoules. When I solve through this, I'm keeping just 1 significant figure, because all throughout my math here, a lot of times I only have 1 significant figure. And so I'm going to round this up to a negative 1,000 kilojoules. And I am solving for this C triple N bond. So now that I'm here and I have 1 mole here, it's really easy to just cancel out that 1, because anything times 1 is the number. But we need to remember that unit for mole. And so the mole part, or the unit part of that, is what is really important here. And so if I take this and I add 1,000 to each side, if I add 1,000 to each side, I actually get 863 kilojoules here. But if I'm sticking with my 1 significant figure, this is 900. Now, since that equals 1 mole, this equals 1 mole times the C triple N bond. Technically, I'm going to divide by mole. And so if I divide by mole, I cancel out mole here. And I'm going to divide by mole here. And the reason that mole is important is because bond energies are per mole. Now going back, and when I was checking what I was doing, I realized that up here I had actually written kilojoules per mole in this part of the problem. And that's because my book has kilojoules per mole as the delta H that it gave. But delta H is just in kilojoules. So if you have a book, you may want to fix that mistake in the text. So your total answer is 900 kilojoules, and that is the bond energy for this for this carbon triple bond to nitrogen. Question number 7 asks you, what is the standard enthalpy of formation for iron in the solid form? And if you're looking for it on the chart, you may have a really hard time finding it, because this iron in its solid form is iron in its natural state. And so the standard enthalpy of formation for any element in its natural state is 0. Question number 8 asked us to determine the delta H for the combustion of C6H6, and that's liquid, and that's at 25 degrees Celsius, and it asked us to use Hess's law. We can use Hess's law at 25 degrees Celsius, and so we're going to use that. That is this law that I have written up here. Remember, it's really long and it feels really complicated, so you should be using a chart that I believe is in the book, or there's one I think in the back cover of the enthalpies of formation for this reaction. But before we can really proceed, we have to write out the reaction because we need to know all the products and all the reactants. So I hope you remember, a combustion reaction always reacts in the presence of oxygen, and it always produces, if it's a complete combustion reaction, water and carbon dioxide. Now, these aren't usually balanced, so we have to balance it. So I have 6 carbons here, and I only have 1. So I'm going to add a 6 here to balance that out. So now I was going to try to balance out the hydrogens here. I have 6 hydrogens, and I have 2 hydrogens. So if I put a 3 here, that gives me 6 hydrogen on each side. So let's look at the oxygens. Here I have 2 oxygens, and on this part, I actually have 3 plus 6 times 2 is 12. So 6 times 2 is 12 plus 3 is 15. So I would want to put a 7.5 here, but as you know, when you balance an equation, you cannot have a decimal, you have to have a whole number. So I'm going to go through and double everything. So 7.5 doubled is 15. Double that becomes a 2, a 6. So I have a 2, a 15, a 6, and a 12, and those feel like really large numbers for balancing, but it all balances out, so we're just going to keep going with it. So then the next part to using Hess's law is I am going to take, similar to what we did in the last time, the number of moles, and this is of the products, and I'm going to multiply it by the delta H of formation that comes from your chart in your book, and then I'm going to subtract the same thing of the reactant. So you do it all for the products, and then you subtract it for the reactants. So for the products, let's start. I actually have 6 moles of water. I'm going to multiply the 6 moles for the water times 241.8 kilojoules per mole. I'm getting that from my textbook. I may put the chart up. We'll see. Okay, so we're going to add our other product, which is for carbon dioxide. I have 12 moles of carbon dioxide. And the delta H of formation for that is negative 393.5. Moles cancels out. So that is for all the products. So I'm going to do the same thing for the reactants. The only thing here is I am subtracting the reactants. So I'm going to do 2 for the C6H6, that's 2 times 49.0 kilojoules per mole. And the next one, I'm going to also subtract 15. And if you'll remember, the delta H for any element in its natural state is 0. Oxygen being in its natural state a homonuclear diatomic, O2 is actually its natural state, and so it has a 0. So since this is just minus 0, I'm going to get rid of it. And you're going to put through in your calculator to solve this for Hess's law. Remember, you have to use parentheses when you put this in, or you will not get the correct answer. And you should get a delta H for this combustion reaction is negative 6,270.8. It is negative because it is releasing and letting go of a lot of heat, and a combustion reaction does that. If you've ever been near anything that's on fire, it is producing a lot of heat. So number 9 is very similar. You're using delta H of formations to calculate Hess's law, but this time we're not calculating the enthalpy. They actually give you the delta H. They're telling you it's 157.9 kilograms. They give you the whole reaction, and they're looking for They're looking for the delta H of formation for H2S, for this compound. So this is kind of similar to question number 6. We're going to do it very similar where we have a unknown variable for this delta H of formation. They also tell me that I have carbon or graphite, and this is its natural state. The other compound that I have in its natural state here is actually hydrogen gas, because H2 or hydrogen is a homonuclear diatomic, and so in that state it's its natural state. So we have two things that the formations are actually going to be 0 for. So we have delta H, which is 157.9 kilograms or kilojoules. And I am going to be using this equation once again. So I have all my products, which I only have one, and it's balanced, and I have 1 mole of that when it's balanced. And from my chart in my book, I am going to be doing the product. So I have CS2, and I have 1 mole of CS2, and it is 116.9 kilojoules per mole is its delta H of formation. Now I would add in my other product, but it is a 0, so that's kind of nice. Now I'm going to take it away for the reactants. So I do subtraction. And so for the reactants, I have carbon or graphite, and we already talked about how the natural state of that one is 0. So we're also then going to do subtracting for the reactants. So the only reactant I'm going to be getting numbers for is the unknown, because graphite is a 0 because it's in its natural state. And so I have 2 moles, and then I just have my unknown delta H. So you're going to try to solve this, and you should get if I simplify it, make it a little bit easier to see, I'm going to subtract 116.9 from both sides. And I get 41.9, and that is equal to negative 2 times the delta H of formation. So I'm just going to move that negative over here, divide that by 2, divide that by 2. 20 equaling the delta H of formation. I think I've made a rounding mistake. It's a little bit different number than they have in the textbook, but it's okay. We're right there at significant figures of 20 as equaling the delta H of the formation for the H2S. Question number 11 actually has 3 parts, and they're asking you to draw 3 reaction coordinates. So I'm not going to put them all on the board at the same time because that would just be a hot mess. But the first part, A, they tell you that it's an exothermic reaction. And so an exothermic reaction is a reaction that releases energy. And so it's losing energy. So the energy is going to be less. And if you'll remember, on our reaction coordinate, this side is basically the energy. And this is like as time progresses throughout the reaction. So I'm going to say it's exothermic. So if it starts down here, it's going to release its energy. It's going to be less. Now it tells me it releases a small amount of energy, so it's not going to lose a huge quantity, so I'm going to put it just a little bit lower. And then it tells me it has a high activation energy, and activation energy is the energy to get the reaction going, and so it's this little hump that you see at the beginning, but it says it's got a high one, so I'm going to draw a big old hump on it. And that would be an exothermic reaction with a high activation energy, and it releases a small amount of energy. So the part B is an endothermic reaction, and that means that this is going to be a reaction that is absorbing heat. So I know that wherever I start, my energy at the end is going to be higher because it's pulling energy into it. The other thing, it tells me that the activation energy is just a little bit bigger than the delta H. And so delta H, remember, is the total energy throughout the thing. And so since the activation energy is just a little bit more, this lets me know that this activation hill is only going to be a little bit higher than the products. Not much. All right, question C, or part C, tells me that this reaction is easier to start than A. So it's easier to start. It's going to have a small activation energy, not a very big one. And it's releasing a lot of energy. It's releasing energy. It's exothermic, so it's going to be losing energy. So its energy out is going to be smaller. It's going to be a big hill down. Question 12 gives you 4 different scenarios, and it asks you to pick which one has the most entropy. If you'll remember, entropy is the amount of disorder or randomness in a system. So we're going to be looking for the part of it that's kind of crazy and has less structure to the system. So this one, we're comparing a vase that is sitting on a shelf to a vase that has been broken, the same exact vase, but it's broken into lots of different pieces. Well, the one that's broken into lots of pieces has a lot more disorder and randomness to it than a vase that is actually like put together on the shelf. Part B tells me I have liquid water and it's at 0 degrees Celsius. And then I have the same amount of liquid of water, but it's in a solid, like an ice cube, at 0 degrees Celsius. I hope you remember from when we studied kinetics that liquids move around a lot more. So it's the same amount of water, same substance, same temperature, but we know that the liquid's going to be moving more, so it's going to have more entropy. The C part says a cold copper pipe or a hot copper pipe. Well, I hope you remember that hot things have more energy and there's a lot more movement, so there's a lot more disorder going on. And C is a bag of confetti, and basically we have 2 separate rooms and it's the same amount of confetti in each room. Just one room is a 3 by 3 meter room and one room is a 2 by 2 meter room. And so the confetti has more space to be spread out in the larger room, and so it's going to be a little bit crazier in a bigger room than it would be in a smaller room. Question number 13 says a student says that because a chemical reaction has a negative delta S, that it cannot be spontaneous. Is the student correct? Well, the student is not correct, because if you'll remember, the second law of thermodynamics, that when it talks about entropy not being able to decrease, it only applies to the entire universe. Well, if I have a negative delta S, yes, entropy is decreasing, but entropy can decrease in a specific reaction, but it just can't decrease in the whole universe. Now, to determine if a reaction is spontaneous or not, we actually have to use the Gibbs free energy equation. And that takes into account the energy that is happening in the reaction and in its surroundings. And so we cannot say that it can't be spontaneous just based on its negative S. You also have to know what's going on with the temperature and its surroundings. Question number 14 gives you 3 reactions and it wants you to determine the sign of S, or the entropy for the reaction. So we're going to look at a few things. We're going to look at the states of the matter, or the phases of the matter in these reactions, and then we're going to look at the number of molecules that's happening. It's not asking you to calculate the whole entropy. It's just asking you to say if it's positive or if it's negative. So in this reaction, I'm going from having a gas and a gas to producing a solid and a gas. And I know that 2 gases are going to have a lot more randomness than a solid is going to have. And so this one is going to have more entropy and this is going to have less. So it's actually going to be losing entropy. So the delta S is going to be negative or less than 0. For part B, I'm also going to start looking by the phase symbols. And first, if I look at the phases, I have 2 gases and I'm going to 1 gas. If we look at the number of molecules, we also have 1 molecule plus 2. So we have 3 molecules going to 1 molecule. Well, 2 gases to 1 gas is losing entropy, and so is 3 molecules to 1. It's actually going to be getting less crazy as we go on. And so delta S for this also is going to be less than 0 or negative. Question C, we have a solid and an aqueous, which is like a liquid, and it's going to produce an aqueous and a gas. And since they both have an aqueous in them, let's look at, we have a solid going to a gas. And so you know that a solid has a lot less craziness going in it and a gas is a lot more. And so this one is going to be becoming more random, more disordered as the reaction proceeds. So for this, delta S is actually going to be greater than 0. And it's going to be a positive number. So for question number 15, we're actually using a reaction we've already did in these review questions, which makes me really happy because it means we don't have to figure it out again and we don't have to balance a new equation. But it tells me in problem number 8, we calculated the delta H for the complete combustion of C6H6. And now it wants us to determine the delta S for that same exact reaction. Well, if you'll remember, the delta S equation is almost identical to the delta H reaction, or to the delta H equation. We're just going to be using different numbers from a different chart in the book. So to first start with the delta S, I'm going to be taking all of the products and I'm subtracting the reactants like I've done normally. So delta S, and so I'm going to take the 12 because I have 12 moles of carbon dioxide, and I'm going to multiply it by a standard that you're pulling from the charts in your book for entropy. And so the standard, or the entropy of carbon dioxide that you get from your chart, is 213.7, and if you'll try to remember, the units for delta S is joules per moles over kelvins. And if you're writing down your cheat sheet or your card or whatever you have for your test, I would make sure I wrote down the units for all of these, because that would actually could help you be able to solve some of these problems. So I've done it for carbon dioxide. Now I'm going to add it for water, and I actually have 6 moles of water, so I'm going to start with 6 times. And when I look up for H2O, and remember the phases matter, I get negative 228.6 joules over moles times kelvins. So those are for the products. So now I'm going to subtract the same thing for the reactants. All right, so when I'm talking about my reactants, I have 2 moles of C6H6, and my constant is 124.4. The other reactant that you have that you should subtract from is using your oxygen, but we've talked about it before. Oxygen as a homonuclear diatomic is its natural state, so it is 0. So I'm going to save a little board space and not keep adding that onto this problem. So now you've solved for delta S. As always, remember those parentheses or you will not end up with the correct answer. As you're solving through this problem, you're going to notice that moles cancels out in all of these. And you're going to get a delta S of 274.8 joules per kelvins. Question number 16 is actually using the same equation again, which makes me really excited because we don't have to, we get to skip a step. But we're going to be calculating the delta G's this time. Ask you to use the Hess law technique. Now that is using basically this equation. Like I said last time in the comprehension check, I did not add on the delta G equation because it's basically this exact same thing, just your constants is for a G and it's different. And so you're going to do very similar to Hess's law. You're just getting your data from a different chart in your book. So make sure that you're using the Gibbs free energy when you when you pull the data from the chart. So we're looking for delta G. So we're going to calculate for the products first. So we have 12 moles of CO2. And you're going to be looking up the Gibbs free energy for CO2 in its gas phase. Gibbs free energy formation for carbon dioxide in its gas phase is negative 394.4 and is in the units of kilojoules per mole. Moles will cancel out. And so the other product that we're going to add is for water, and we have 6 of those. When you look it up for water, you get negative 228.6, and we're going to cross out moles. And we're going to subtract the product or the reactants. And so just like the last time, we actually have oxygen as a reactant. So we're saving a little bit of math because oxygen is 0. So we're going to do just the 2 moles, and you're going to be multiplying it by 124.4. Now, go ahead, put it in your calculator. I would recommend pausing it and checking it instead of just like copying what I'm doing. And let's see what you got for delta G. And for delta G, I get negative 6,353.2 kilojoules. The other part of the question is it asks if it's spontaneous. And if you'll remember, if delta G is negative, it is spontaneous. So this reaction will proceed. Question 17 is another one of these problems that has 4 parts. I get excited when I look and I see only 20 problems, and when I realize that like most of the problems have 4 parts to them. I feel like it's a little trickery that they do. But anyways, so number 17, we're basically going to do the same thing 4 times in a row, so you'll get lots of extra practice. But it gives you the delta H and the delta S for several different reactions. It wants you to determine if the reaction is spontaneous at all temperatures. So we're going to use the Gibbs free energy to determine if it's spontaneous. It wants us to say, is it spontaneous at all temperatures? Is it never spontaneous? It doesn't matter what the temperature is. Or is it spontaneous for a range of temperatures? If it's spontaneous for a range of temperatures, give the range. So we're going to use this Gibbs free energy equation for this. And to be spontaneous, delta G has to be a negative. So I'm going to say if delta G must be negative to be spontaneous, I'm going to use this equation, but I'm going to set it up equal to being less than 0 because less than 0 is negative. So I'm going to say it has to be less than 0, and then the delta H minus the time, or minus the temperature. We don't know the temperature, that's what we're trying to figure out. And the delta S, which they give you. Now, if you'll look, if I was to solve this problem the way it is, my units would not cancel out properly because I have a kilojoules and I have a joules. So I need to put this into joules. So I'm just going to move my decimal 3 places over to the right so that all my units are in joules, so I have the right units at the end of the problem. So I'm going to subtract 146,100 joules from both sides. So over here you get all right, once I've subtracted and moved this over, to get T alone, I'm going to divide by 86.1. And my joules cancel out, and since I have a negative on both sides, that's going to cancel out. 1.7 times 10 to the third kelvins. So the temperature must be greater than this in order for this reaction to be spontaneous. So let's figure this out for question B. Let's go ahead and put kilojoules as joules. And so I'm going to fill in for delta G just to see what it looks like. Now, if you'll remember that temperature is in Kelvin, so we cannot have a negative Kelvin temperature. So this temperature here is not going to change the sign. So when I have a negative number and I'm going to be subtracting a negative number, I am always going to have an answer that is negative. So this reaction is going to be spontaneous across all temperatures. It doesn't matter what number I put in here. I'm going to have a negative minus a negative. For C, we have a delta H of 219.5 kilojoules. We're going to go ahead and move that over to being joules. Good habit to have. And negative 99.9 is our entropy. And so let's go ahead and plug this in and see what this looks like. For C, this was a bit confusing for me at first, but I had to think about temperature. The temperature is in kelvins in these, and so temperature can never be negative. It can only be a zero, like a positive number. And so for this, if temperature is always going to be a positive number, I am always going to be subtracting a negative, which means I'm always going to be adding a positive. Right? Subtracting a negative is adding a positive. Since I will always be adding a positive in this equation, delta G is always going to be positive. And so this reaction is never going to be spontaneous. All right, this is the last one of these. If you're stuck on these are hard and kind of confusing. It does talk about it in the very last section of the book, but let's try and figure this one out. So next step, let's make this be joules. And we're going to write this for delta G. So we have, so when I put this in for delta G, if I have like negative 419,000, and then I would be subtracting a negative, because remember this is never going to be negative. If I'm subtracting a negative, it's like I'm adding. So I have a negative number and I'm adding to it. There is a chance that delta G could still be negative, right? I could add up to 399, and delta G will still be negative. So let's figure out the temperature range at which this reaction would be spontaneous, or delta G would be negative. So we're going to set it equal to being less than 0, because if this is less than 0, then it will be negative. So I'm going to add the 419 and 400 joules to each side. Because it's negative, I'm going to add it. And now I'm going to divide by the negative 114. to get T alone. Joules is going to cancel out. And I've got a negative number here and a negative number here. So I've got a negative number here and a negative number here. So I'm just going to get rid of those. When you put this in your calculator, the temperature must be bigger than 3,676 kelvins in order for this reaction to be spontaneous. Question number 18 tells me which is not zero for an element in its natural phase. Is it the delta H, the entropy, or the Gibbs free energy? The entropy. This is entropy. If you'll remember, this is not a delta S. This is just the straight entropy of anything, and it's not going to be zero. Nothing has zero entropy or zero disorder to it. Question number 19 says you and a friend are going to the store. You each leave at the same time and you take a different route to the store and you arrive before your friend. What is a state function? Well, if you remember all about state functions, it doesn't matter about the path that you take. So let's look and see what will be affected by the path, and that is not a state function. So the path you traveled is clearly not a state function, and the time it takes depends on the path you travel. So this is not a state function, but your destination, because your destination does not matter how you got there. All that matters is that you got there. So this would be considered a state function. Question 20 tells me we have a physical process in a system and it's cooling down its surroundings and it's a spontaneous reaction. And so it's asking you, is it having an increase or a decrease in enthalpy? Well, I'm actually going to go back to this equation because it tells me it's spontaneous. So I know delta G is negative. Since it's cooling its surroundings, it is actually pulling heat into it. And so the delta H is going to be positive. And I'm subtracting the temperature times the delta S. It's real rough looking here, but I have negative delta G. So in order to get a negative, I have a positive number, and it has to subtract to get a negative. So if a positive number, if delta S was a negative, this would make minus a negative. It would be a positive, right? And so a positive and a positive would not equal a negative. But if delta S was a positive number, and we had a positive number minus a positive number, we could get negative. So delta S would have to be a positive number. So therefore, you would have an increase of entropy into this system. You guys have done a great job and you're almost done with the book.